Hello, I'm Collin Dunn, and this summer I've been working with Dr. Novomir Pablant to study the effects of thermal deformation on ITER's X-ray spectroscopy system. To help you understand my project, I'd like to give a little background on X-ray crystal spectroscopy. The XRCS is a diagnostic used on tokamaks and stellarators to measure ion temperature profiles, electron temperature profiles, and colloidal flow velocity profiles. High Z impurities found or introduced in the plasma, like xenon and tungsten, emit X-rays with discrete known wavelengths. The spectra these X-rays produce is measured by a detector. As temperature in the plasma increases, the emission peaks widen, thus allowing for the ion temperature to be determined by measuring the Doppler width of these peaks. Also, as the plasma moves faster, these emissions undergo a Doppler line shift, allowing for the colloidal flow velocity to also be measured. X-ray crystal spectroscopy is also advantageous over other diagnostics in that it can measure ion temperature even at the core of dense plasmas and can be used continuously during long plasma shots. Currently, there is a plan to construct an X-ray crystal spectroscopy system in ITER. However, due to spatial constraints, this system must fit in a narrow, tight shaft. But ITER engineers and scientists have developed a system that meets this criteria by using special HOPG pre-reflectors. This system uses 16 sight lines, shown in the dashed lines on the left, to ensure measurements covering the full minor radius can be taken. Additionally, the design places the crystals and detectors behind the bioshield, thus protecting them from radiation. An issue with this design for ITER is that the system could be very sensitive to changes in the positioning of the optical devices. And since ITER will be heating up plasmas to hotter than the sun, you can be sure there will be large heat fluxes on the system, resulting in thermal deformation. The objective of my project was to understand the effects of this thermal deformation on the XRCS system. I accomplished this objective by studying the effects of geometric translations and rotations of the pre-reflector on throughput and bandwidth, and by using the thermal deformation models created by ITER engineers to simulate the XRCS system. The system was modeled using the XICSRT Python package developed for X-ray ray tracing. I developed a simple model that used a planar X-ray source instead of the full plasma, and only included one pre-reflector, crystal, and detector. Nonetheless, all of the dimensions and coordinates for each of the optical components were identical to the ITER XRCS core dimensions. The model is pictured on the right with two different views, a side view and a top view. The potential effects of thermal deformation were modeled by simple on-axis translations and rotations of the pre-reflector. The XICSRT Python module was developed in part by my mentor, Dr. Pablant, and it is an advanced X-ray ray tracing code that can model complex crystal shapes, multi-layer HOPG reflectors with specific mosaicity and rocking curves. The code calculates the Bragg angle at each X-ray material interaction and uses probability distributions to determine if a ray makes it through. This code allowed me to accurately simulate millions to billions of X-rays in my model. Using the XICSRT code with the simplified planar source model, I performed simulations of translating the position of the reflector along the global X, Y, and Z axes. The Y-axis translations had almost no effect on the throughput, as can be seen in the figure. But the X and Z-axis translations did significantly reduce throughput, but only after about 2 centimeters of translation, which is a larger displacement than is expected in the XRCS core system. I also studied the effect of rotations on the reflector. The throughput of the detector is much more sensitive to rotations than translations, especially rotations about the local x-axis, as can be seen in the figure in the middle. As you can see in the animation, as the pre-reflector is rotated, the rays, shown as white dots, change their average location on the crystal. And as these movements increase, as can be seen in the figure on the right, the X-ray bundle shifts, and fewer X-rays reach the detector, thus leading to a smaller throughput. In studying the effects of rotation and translation on the detector bandwidth, I found that rays from different sightlines form different detected wavelength distributions. The blue and red sightlines produced a plateaued wavelength distribution of detected rays, which was expected. However, the yellow and magenta chords formed a more pointed distribution, which was unexpected and led to greater sensitivity to reflector tilt. The distinguishing feature between these different chords was the location of their pre-reflectors. The yellow and magenta pre-reflectors are located at the top of the XRCS core system, whereas the blue and red pre-reflectors are located at the bottom. However, this does not entirely explain the behavior, and further research is needed to determine why these chords form this pointed distribution. By using a source with a uniform distribution of wavelengths, the bandwidth of the detector was modeled, and the differences seen in the previous slide become much more apparent when reflector tilt is introduced. As can be seen in the top left animation, the red chord did not change its distribution shape much as the pre-reflector was rotated. Only its intensity appeared to change. However, as reflector tilt increased, the magenta 1 chord wavelength distribution became more and more skewed, as seen in the top right animation. Looking at the full width half max bandwidth, representing 76.1% of the data, as shown in the bottom right figure, the red 1 chord did not change much as the pre-reflector was rotated, but there was a significant drop-off in the bandwidth of the magenta 1 chord. A couple of potential solutions to this bandwidth problem were suggested. One was to increase the pre-reflector rocking curve spread. As seen in the figure, increasing the rocking curve full width half max substantially increased the throughput, but did not change the skewing behavior that occurred as the pre-reflector experienced tilt. Another proposed solution was to change the crystal size. Similar to the rocking curve results, increasing the crystal size increased overall throughput and changed the spread, but it did not alter the skewing behavior. Thus far, all of the results I have presented were found using generalized rotations and translations, rather than the specific thermal deformations that would occur on the system. Having been given a tolerance of 0.1 degrees previously, ITER engineers designed a system to house the blue and red chord pre-reflectors and model the thermal deformation of that system under heat loads. Using this data, I ran simulations of the XRCS core system under the cold and hot conditions, and the results were very promising. The distributions of the cold and hot systems had very similar shapes and statistics. Only the overall intensity was somewhat reduced in the hot system. So, to summarize, I found that small translations of the pre-reflector result in minimal effects to the detector throughput. However, small rotations of the reflector can not only negatively affect throughput, but also skew the wavelength distribution and reduce the detector bandwidth. These results are concerning since ion temperature profiles and velocity profiles depend on having a well-calibrated and well-understood line widths and line shifts. However, using the previously determined 0.1 degree tolerance, it appears that the sight lines thus far studied do not undergo dramatic changes in their wavelength distributions. To run this diagnostic successfully in ITER, we must do future work to understand why particular sight lines produce pointed distributions, and see what the effect of thermal deformation is for these chords, specifically on their effect on plasma velocity and ion temperature calculations. Thank you for listening.